Hey everyone, welcome back to the channel. Before we dive into this absolutely mind-blowing journey through the cosmos, make sure you hit that subscribe button and give this video a like. It really helps the channel, and trust me, what I'm about to tell you will completely change how you see the universe and our place within it. Right now, you are falling through a hole in space 2 billion light-years wide. Scientists confirmed this in 2013, and most people still have no idea. We live inside the KBC Void, a cosmic desert where matter is 20% thinner than it should be. This emptiness is warping our measurements of reality itself. The universe appears to expand faster here than anywhere else, breaking our most fundamental equations. We will journey through the discovery that shattered cosmology, explore why 90% of space is hollow, and reveal what it means to exist in the cosmic outskirts. If you are ready to see the universe differently, hit that like button and subscribe. Prepare yourselves. We begin. 3 astronomers were counting galaxies when they noticed something impossible. Ryan Keenan, Amy Barger, and Lennox Cowie examined 35,000 galaxies in 2013, mapping their positions across billions of light-years. The numbers were wrong. Everywhere they looked near Earth, there were fewer galaxies than there should be, not slightly fewer, but 20% fewer. The pattern stretched outward in every direction for a billion light-years, forming a sphere of cosmic emptiness with us near the center. This was not a small gap between galaxy clusters. This was a void on a scale that should not exist according to standard cosmology. The researchers triple-checked their data, used multiple galaxy surveys, and examined the sky from different angles. The result remained consistent. Our galaxy and everything around it sits inside an underdense bubble of space so massive it dwarfs everything else we have ever observed. The discovery earned a name that sounds almost casual, the KBC Void, using the initials of its 3 discoverers, but there is nothing casual about what it represents. In the standard model of cosmology, the universe should be roughly uniform when you zoom out far enough. Sure, galaxies cluster together and leave empty spaces between them. That is expected. But a region this enormous, with such a significant deficit of matter, pushes the boundaries of what random chance can explain. Computer simulations of how the universe evolved from the Big Bang rarely produce voids this large and this empty. When they do, it requires exceptionally rare initial conditions. The statistical probability is less than 1 in 1,000. Some scientists calculated it would take a 10 sigma deviation from average density, meaning it is so unlikely that you might not find one in the entire observable universe. Yet here we are, living inside one. The implications began cascading immediately. If we reside in such an unusual location, does that bias every measurement we make? When we point our telescopes at distant supernovae to measure how fast the universe expands, are we seeing the true cosmic expansion rate or a distorted local version? The void hypothesis offered an answer to one of the biggest mysteries in modern cosmology, the Hubble tension. For years, scientists have measured 2 different expansion rates depending on whether they look at the ancient universe or the nearby universe. The numbers disagree by 9%. That sounds small but represents a crisis. Both measurements are incredibly precise. Both should give the same answer. They do not. If Earth sits inside a massive underdense region, gravity from the denser matter surrounding the void would pull outward on galaxies within it. That would add extra velocity to their motion away from us, making the local expansion appear faster than average. Suddenly, the conflicting measurements made sense. We are not measuring the universe incorrectly. We are measuring it from inside a hole. This realization changed everything. But it also raised an uncomfortable question that cosmologists are still grappling with. If our location is this unusual, can we trust anything we think we know about the cosmos? What comes next reveals just how strange our cosmic neighborhood really is. Cosmic voids are not truly empty, which makes them even stranger than their name suggests. Between these lonely galaxies stretches space that contains mainly dark matter, dark energy, and occasional wisps of hydrogen gas. The density is so low that gravity barely functions. Without enough mass to pull things together, structure formation essentially stops. No new galaxy clusters can form. No rich superclusters emerge. The void stays a void. This emptiness has consequences that ripple through physics itself. Gravity is already the weakest fundamental force in nature, requiring enormous masses like planets and stars to show noticeable effects. In a void where mass is scarce, gravity becomes even less relevant. The dominant force becomes dark energy, the mysterious pressure that accelerates cosmic expansion. In dense regions full of galaxies, gravity fights against dark energy, slowing down the expansion in those areas. Inside voids, gravity loses that tug of war. Dark energy wins decisively. As a result, voids expand faster than the rest of the universe. They grow like bubbles, pushing their boundaries outward, while the filaments of galaxies around them act as walls. This creates a self-reinforcing cycle. The more a void expands, the emptier it becomes, which allows even faster expansion. Scientists confirmed this through careful observation. They measured how galaxies near void edges move compared to galaxies in denser regions. The void galaxies are rushing away from the center faster than cosmic expansion alone would explain. Something is pushing them outward. That something is the gravitational pull from all the matter outside the void. Think of a void as a valley surrounded by mountains. Gravity pulls downhill from the mountains toward the valley. But since we are talking about space rather than terrain, that pull makes galaxies fall outward, not inward. The effect is measurable and significant. Our own galaxy is moving away from the local void at 600,000 miles per hour, driven by this gravitational imbalance. The interior of a void becomes a strange place for physics. Light travels through it, experiencing less gravitational influence than light passing through normal space. This affects observations in subtle ways. When astronomers study the cosmic microwave background radiation, the faint afterglow of the Big Bang, they notice that light passing through voids appears slightly cooler. The reduced gravity in voids causes less gravitational redshift, showing up as cold spots in temperature maps of the early universe. These cold spots line up perfectly with where we observe large voids today. This alignment is not coincidence. It is physics. Understanding what makes voids empty helps explain why they matter so much to cosmology. They are not just boring blank spaces between interesting galaxy clusters. They are laboratories where dark energy dominates and where gravity takes a backseat. By studying how matter behaves differently in voids versus dense regions, scientists can test fundamental theories about how the universe works. The KBC void around us might be unsettling because it makes us question our cosmic typicality, but it also offers a rare opportunity. We are positioned in exactly the right place to study the universe's most extreme low-density environments. The structure that contains these voids is far stranger than anyone imagined. The universe is not a smooth soup of evenly distributed galaxies. Instead, it resembles Swiss cheese, where dense matter forms walls and filaments surrounding enormous hollow pockets. This foam-like architecture is called the cosmic web, and it represents the largest structure in nature. Galaxy clusters concentrate at the intersections where multiple filaments meet, creating nodes of intense matter density. These nodes shine brilliantly with millions of galaxies packed relatively close together. Stretching between them run filaments, long chains of galaxy groups that can extend for hundreds of millions of light-years. These filaments form walls, vast sheets where galaxies gather in higher than average concentrations. Between the filaments and walls lie the voids, taking up most of the volume while containing hardly any mass. This structure was not always obvious. For decades, astronomers photographed the sky and counted galaxies, but the true three-dimensional arrangement remained hidden. Distance measurements were poor. Galaxies that appeared next to each other might actually be separated by billions of light-years, with one much farther away than the other. Only when scientists began measuring galaxy redshifts systematically in the 1970s and 1980s did the cosmic web reveal itself. Redshift surveys allowed astronomers to calculate how far away each galaxy was by measuring how much the expansion of space had stretched its light toward redder wavelengths. Suddenly, the distribution snapped into focus. The universe had structure on scales nobody expected. The first major void discovery came in 1978 when two independent teams identified large underdense regions. More surveys followed, each mapping deeper into space and revealing an increasingly intricate web. The Sloan Digital Sky Survey, which began in 2000, created spectacular three-dimensional maps spanning billions of light-years. These maps show the cosmic web in stunning detail. Filaments twist and branch like blood vessels. Voids appear as dark bubbles, sometimes 500 million light-years across. The largest structures include the Sloan Great Wall, a filament nearly 1.5 billion light-years long. On the opposite end of the spectrum, supervoids like the Eridanus Void stretch 1.8 billion light-years wide with even fewer galaxies than the KBC Void. Together, these features paint a picture of a universe organized on scales far larger than anyone predicted. Galaxies are not the fundamental building blocks. The web itself is the structure, with galaxies just marking where the matter happens to concentrate. Why does the universe organize this way? The answer reaches back to the beginning. Immediately after the Big Bang, matter was not perfectly uniform. Quantum fluctuations during the universe's first fraction of a second created tiny variations in density. Some regions slightly denser than average and others slightly less dense. These differences were minuscule, maybe 1 part in 100,000, but gravity amplifies even tiny advantages. Denser regions pulled in more matter, making them denser still. Less dense regions lost matter to their surroundings, becoming emptier. Over hundreds of millions of years, this process snowballed. Small clumps merged into larger clumps, which merged into galaxy clusters, which aligned into filaments. Meanwhile, the underdense regions expanded into voids. The cosmic web is essentially gravity doing its work over cosmic time, turning barely noticeable initial ripples into the grandest architecture in existence. Today, voids occupy roughly 90% of the volume of space. Filaments and clusters make up the remaining 10%, but contain most of the mass. This imbalance defines the universe's character. We live not in a cosmos filled with galaxies, but in a cosmos of emptiness punctuated by occasional concentrations of matter. The KBC Void is just one bubble in this foam, but it happens to be our bubble, and that makes all the difference for what we observe and how we interpret the universe. The next chapter reveals exactly where we sit inside this immense hollow. The Milky Way is not at the center of the KBC Void, but it is close enough to matter. Measurements place our galaxy somewhere between 200 and 400 million light-years from the void's actual center. That might sound like a huge distance, and it is compared to anything humans experience. But the void extends outward for 1 billion light-years in every direction from its center, making our offset relatively small. We sit well within the underdense region, surrounded by the void's low-density environment in all directions. This position is not random. It has consequences for every observation we make and every conclusion we draw about cosmology. If we were located outside the void entirely in one of the dense filaments, our measurements of the universe's expansion would look completely different. We would calculate a slower expansion rate, and the Hubble tension would not exist. Our larger cosmic neighborhood adds another layer to this story. The Milky Way belongs to the local group, a collection of about 80 galaxies, including our giant neighbor Andromeda. The local group itself sits within the Laniakea supercluster, a massive structure containing roughly 100,000 galaxies spread across 520 million light-years. Laniakea is enormous by any normal standard. Yet even this supercluster resides within the KBC Void. Think about that for a moment. A structure containing 100,000 galaxies still counts as part of an underdense region. The void is so vast that it can swallow entire superclusters and still have room to spare. Laniakea forms part of the sparse population of matter scattered through the void, one of the rare concentrations in an otherwise barren expanse. The local group is also influenced by another nearby void called the local void, which is distinct from but connected to the larger KBC Void. The local void extends about 200 million light-years and sits adjacent to our position. Our galaxy is rushing away from it at 600,000 miles per hour, pushed by the gravitational pull from denser regions beyond. This motion is separate from the overall cosmic expansion. It is a peculiar velocity, meaning it results from local gravitational effects rather than the stretching of space itself. These peculiar velocities complicate efforts to measure the true expansion rate because they add extra motion on top of the expansion signal. Astronomers must carefully account for these local effects. But inside a supervoid, those effects are amplified and harder to separate cleanly. The void's influence reaches even farther. When scientists measure the motion of galaxies out to distances of 250 million light-years, they find bulk flows that exceed predictions from standard cosmology. Entire regions of space are moving faster than they should be, flowing in coherent patterns driven by the void's gravitational imbalance. The KBC Void creates a large-scale velocity field that affects everything within it. Galaxies are not just sitting in an empty region, passively expanding with the universe. They are actively responding to the gravitational landscape, accelerating outward from the underdensity toward denser structures beyond the void's edge. This makes our local patch of the universe more dynamic and unusual than the calm, uniform cosmos that standard models assume. Our position inside the void also affects what we can see. Light from distant galaxies travels through the void on its way to our telescopes. That light experiences less gravitational interaction than light traveling through denser regions. The reduced gravity creates subtle effects on the light's wavelength and energy. Additionally, the void itself influences the distribution of matter we observe. When we look outward from inside the void, we see the shell of denser material surrounding us in all directions. That shell appears as a concentration of galaxy clusters and filaments at a specific distance range. Beyond the shell, the universe returns to more typical density. This creates an observational bias. We are not sampling a random location in the universe. We are sampling from inside one of its most extreme features. Living in the void means living with systematic uncertainty about how typical our measurements really are. Every measurement you have ever heard about the universe's expansion rate might be wrong. Not because scientists made mistakes, but because we are measuring from inside a cosmic hole that distorts the signal. The problem reveals itself when astronomers use different methods to calculate the Hubble constant, the number that tells us how fast space expands. One method looks at the cosmic microwave background, ancient light from when the universe was just 380,000 years old. This light encodes information about the early universe's density and expansion rate. Scientists feed this data into cosmological models and calculate what the expansion rate should be today. The answer comes out to about 67 kilometers per second per megaparsec. That means for every megaparsec of distance, roughly 3.3 million light-years, space expands at 67 kilometers per second. The second method looks at nearby objects with known brightness, specifically type Ia supernovae and Cepheid variable stars. These objects serve as cosmic measuring sticks because astronomers understand exactly how bright they should be. By comparing their actual brightness to their apparent brightness as seen from Earth, scientists calculate their distance. Combining distance measurements with redshift measurements gives the expansion rate directly. This local method consistently produces a higher number, about 73 kilometers per second per megaparsec. The difference is 9%. Both measurements are incredibly precise with very small error margins. Both should give the same answer if cosmology is correct. They do not. This discrepancy is the Hubble tension, and it has reached 5 sigma statistical significance, meaning there is less than a 1 in a million chance it is just random variation. The KBC void explains why these numbers disagree. When we measure the expansion rate using nearby supernovae, we are measuring within the void. The void's low density means less gravity pulling back on the expansion. Matter from the denser regions outside the void gravitationally attracts galaxies within it, adding extra outward velocity. Galaxies appear to recede faster than they would in a typical region. This inflates the local Hubble constant measurement. We are not measuring the universe's true expansion rate. We are measuring the expansion rate plus the void's peculiar velocity field. The effect is large enough to account for most or all of the observed tension. When scientists model how a void of the KBC size and depth would affect local measurements, they find it could boost the apparent expansion rate by exactly the amount needed to match observations. But here is where it gets uncomfortable. If the void explains our local measurements, then those measurements might be systematically biased by our location. Some scientists resist this conclusion because it violates the cosmological principle, the assumption that Earth does not occupy a special location. The principle states that the universe should look roughly the same from any vantage point once you average over large enough scales. Finding ourselves inside a supervoid that significantly affects our measurements seems to contradict that idea. It suggests we are in an unusual location, which makes physicists uncomfortable. Science has progressively decentered humanity from special cosmic positions. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The galaxy is not the center of anything. And now we are supposed to believe we just happen to live inside one of the largest voids ever observed. The statistical improbability bothers many researchers. Yet the evidence keeps mounting. The void exists. Our measurements are discrepant. The void's effects match the observations. Whether we like the implications or not, the universe might actually be lying to us about its expansion rate. Or, more precisely, our location is causing us to misinterpret what we measure. The crisis this creates in cosmology runs deeper than most people realize. The Hubble tension is not just an inconvenient disagreement between two measurements. It represents a fundamental challenge to our understanding of cosmic evolution. Cosmology rests on a framework called lambda cold dark matter, or the Standard Model of Cosmology. This model has been spectacularly successful at explaining observations from multiple sources. It accounts for the cosmic microwave background temperature fluctuations, the abundance of light elements like hydrogen and helium, the formation of galaxies, and the large-scale structure of the universe. For decades, it has been the consensus model because it works so well in so many contexts. But the Hubble tension suggests something is missing or wrong in this framework. When a model's predictions disagree with observations at the 5 sigma level, scientists must take that seriously. The tension matters because the expansion rate determines everything else about cosmic history. If the universe expands faster, it reaches its current size in less time, making the universe younger. Current calculations based on the cosmic microwave background put the universe's age at 13.8 billion years. But if the higher local measurement is correct globally, the universe might be only 12.7 billion years old. That creates immediate problems. We observe stars in globular clusters that appear to be 13 billion years old based on stellar evolution models. These stars would be older than the universe itself, which is impossible. Either our age measurements for stars are wrong, our understanding of stellar physics is wrong, or the higher Hubble constant does not apply to the early universe. None of these options are comfortable. The tension also affects our understanding of dark energy, the mysterious force accelerating cosmic expansion. Dark energy makes up about 68% of the universe's total energy content according to standard models, but its properties depend sensitively on the expansion rate. If the expansion rate is higher than we thought, dark energy's behavior might be different than current models assume. Some researchers have proposed that dark energy evolves over time rather than being constant, which would be revolutionary. Others suggest we need to add new physics to the early universe, perhaps an extra burst of accelerated expansion shortly after the Big Bang. Every proposed solution introduces new complications and requires evidence beyond just fixing the Hubble tension. Dozens of alternative explanations have been put forward. Some scientists propose that the measurements themselves contain subtle systematic errors that have been overlooked. Perhaps dust between galaxies dims supernovae more than accounted for, making them appear farther away and inflating the expansion rate. Or maybe Cepheid variable stars behave differently in different environments, biasing their use as distance indicators. These explanations keep getting tested and ruled out as measurement techniques improve. The measurements are solid. Other researchers suggest modifications to general relativity, Einstein's theory of gravity. Maybe gravity works slightly differently on cosmological scales than we think, which would change predictions for expansion. This route leads into controversial territory because general relativity has passed every other test thrown at it. The void hypothesis offers a cleaner solution that requires less modification to fundamental physics. It simply states that we are in an unusual location and our local measurements reflect that rather than reflecting universal properties. This explanation bothers people philosophically but requires fewer assumptions than inventing new particles or changing gravity. Recent work has strengthened the void hypothesis by showing it naturally predicts other observations. For example, the outflow velocity from the void should affect not just the expansion rate, but also the motion of galaxy clusters in our vicinity. Measurements of these bulk flows match the void predictions. The hypothesis is making testable predictions that are being confirmed. Nevertheless, debate continues. Not all cosmologists accept the void explanation. Some argue that even a void as large as the KBC cannot produce a big enough effect to fully explain the tension. Others point out that supervoids this large should be rare, and finding ourselves in one just when we develop the precision to measure the Hubble constant seems suspicious. Maybe we are interpreting the data incorrectly somehow. The controversy remains unresolved, which is why the Hubble tension continues to be called a crisis. It is not just a number that is off. It is a signal that our understanding of the cosmos might be incomplete. Understanding how gravity creates this mess requires looking at how forces work in empty space. Gravity inside a void does something counterintuitive, pushes outward instead of pulling inward. This is not because gravity itself reverses. The force of gravity always attracts mass toward mass. But the geometry matters. Imagine standing in a shallow valley surrounded by mountains. Gravity pulls you toward the mountains, which means pulling you away from the valley center. Inside a cosmic void, galaxies experience the same effect. All the matter lies outside the void in the surrounding filaments and clusters. That exterior matter gravitationally attracts the interior material, pulling galaxies outward from the void center toward the denser regions beyond. The result is an outflow, a systematic pattern of galaxies accelerating away from the underdense region. This outflow is measurable and significant. Astronomers can track galaxy velocities using redshift measurements combined with distance estimates. When they map velocities around known voids, the pattern is clear. Galaxies near void centers are moving faster outward than cosmic expansion alone predicts. The effect is strongest near the void center and weakens toward the edges where matter density increases. For the KBC void specifically, the outflow adds hundreds of kilometers per second to galaxy velocities within the void. Our own galaxy participates in this pattern. The Milky Way is moving at 600,000 miles per hour away from the nearby local void, driven by the gravitational imbalance. This motion combines with other local effects like the gravitational pull from the Virgo cluster to create our galaxy's overall peculiar velocity. The outflow has implications for cosmic expansion measurements. When we observe distant galaxies and measure their redshift, we are seeing a combination of two effects: the expansion of space itself and the peculiar motion of galaxies due to gravity. Normally, scientists can separate these components because peculiar velocities average out when you look at large enough volumes. For every galaxy moving toward you due to local gravity, another galaxy is moving away, and the average is zero. But inside a void, the peculiar velocities do not average out. They all point in the same direction, outward. This creates a systematic bias that inflates the apparent expansion rate when measured from within the void. The problem compounds at different distance scales. Close to the void center, the outflow is rapid. Farther from the center but still within the void, the outflow is slower. Beyond the void's edge, the peculiar velocities might even reverse as matter falls back toward the denser filaments. This creates a complicated velocity profile that varies with distance. When astronomers measure the Hubble constant using supernovae at different distances, they are sampling this varying velocity field. If most of their supernovae lie within the void, which they do because we deliberately avoid using extremely distant supernovae due to other complications, the measurement gets boosted by the outflow. The further out you measure, the less the void affects the result. This predicts that the Hubble constant should appear to decrease with distance, and recent observations confirm exactly that trend. Modeling these effects requires careful calculation. Scientists must estimate the void size, depth, and density profile, then calculate the gravitational potential it creates. That potential determines how fast material flows outward at each radius. The calculations show that a void roughly 1 billion light-years in radius with a 20% density deficit can easily produce the observed velocity anomalies. The match between predictions and observations is good enough that many researchers find the void explanation compelling. However, the standard cosmological model struggles to explain how such a large void formed in the first place. Computer simulations based on lambda cold dark matter rarely produce voids this extreme. When they do, it requires very specific initial conditions that are statistically unlikely. This raises a troubling possibility. Maybe our cosmological model is missing something. If voids larger and deeper than expected keep showing up in observations, perhaps structure formation works differently than standard theory predicts. Some scientists propose modified gravity theories where gravity is stronger on large scales, which would enhance structure formation and make big voids more common. Others suggest that the universe is simply more inhomogeneous than assumed, which would also make large voids less surprising. Either way, the backwards gravity in voids is telling us something important about cosmic evolution. Our motion through this gravitational landscape is faster than anyone expected. The Milky Way is not sitting still in space. It is plummeting through the cosmos at 600,000 miles per hour, roughly 850 times the speed of sound. This velocity is not from the expansion of space, but from local gravitational effects. Specifically, our galaxy is being pulled away from the local void and toward the denser structures beyond it. The local void is distinct from but connected to the larger KBC void, and it exerts a strong influence on our motion. The void itself is not pushing us. Rather, the deficit of matter in the void means there is less gravity pulling us toward it compared to the gravity pulling us in other directions. The denser regions win the tug of war, accelerating our galaxy away from the underdensity. This speed is difficult to comprehend. 600,000 miles per hour means the Milky Way travels about 167 miles every second. In a single year, our galaxy moves about 5.2 billion miles through space relative to the void. But even at this breakneck pace, the void is so vast that our motion barely makes a dent. It would take hundreds of millions of years to cross from one side of the void to the other, even at this speed. Meanwhile, the void continues expanding due to cosmic expansion and dark energy, growing faster than we can escape it. We are inside the void now, and we will remain inside it for the foreseeable cosmic future. The local sheet adds another component to our motion. The local sheet is a flattened structure of galaxies that includes the Milky Way, Andromeda, and other nearby galaxies. This sheet forms one wall of the local void. The entire sheet is rushing away from the void center at about 260 kilometers per second, which is roughly 580,000 miles per hour. Our galaxy participates in this bulk motion along with its neighbors. The sheet is not static. It is actively being evacuated from the void region, flowing outward like water draining from a depression. This motion has been ongoing for billions of years and will continue for billions more. But there is more to our velocity than just escaping the void. The Milky Way is also falling toward the Virgo cluster, a rich concentration of galaxies about 60 million light-years away. The Virgo cluster contains over 2,000 galaxies and has enough mass to gravitationally attract everything in the surrounding region, including us. This adds another component to our peculiar velocity, roughly 250 kilometers per second directed toward Virgo. Meanwhile, the Milky Way and Andromeda are falling toward each other and will collide in about 4 billion years. That motion adds yet another velocity component. When you add up all these gravitational influences, the Milky Way's total peculiar velocity relative to the cosmic microwave background rest frame is about 627 kilometers per second. That is the velocity astronomers measure when they look at the dipole pattern in the cosmic microwave background temperature. These motions matter because they complicate cosmological measurements. When we observe distant galaxies and measure their redshift, we need to correct for our own motion through space. Otherwise, galaxies in the direction we are moving appear blue-shifted, and galaxies in the opposite direction appear redshifted, creating a false pattern that mimics cosmic structure. Astronomers have known about these corrections for decades and routinely apply them. But inside a void, the corrections become more complicated because the void itself creates large-scale bulk flows that extend over hundreds of millions of light-years. Disentangling the void effect from the true cosmic expansion requires careful modeling of the local velocity field. Our high speed through space is itself evidence for the void. If we lived in a typical region with average density, our peculiar velocity would be much smaller, maybe 100 or 200 kilometers per second at most. The fact that we are moving so fast indicates strong gravitational gradients in our vicinity, exactly what you would expect from being near a large underdense region. The velocity is consistent with the void hypothesis and would be difficult to explain without it. This makes our motion a key piece of evidence in the debate over whether the KBC void exists and whether it affects our measurements. The universe may be lying to us about its expansion rate, but it cannot hide the fact that we are racing through it at incredible speed. This motion connects to a deeper principle that the void fundamentally violates. The cosmological principle is one of the foundational assumptions of modern physics, and the KBC void threatens to shatter it. The principle states that the universe is homogeneous and isotropic on sufficiently large scales. Homogeneous means the same everywhere. No location is special or different from any other when you average over large regions. Isotropic means the same in all directions. The universe looks the same no matter which way you look. These assumptions simplify the mathematics of cosmology enormously. They allow scientists to model the entire universe using relatively straightforward equations. Without the cosmological principle, the equations become vastly more complicated and predictions become much harder to make. The principle has been remarkably successful, accurately describing many observations. But the KBC void represents a major violation of homogeneity. If the void is 2 billion light-years across with a 20% density deficit, that is a huge inhomogeneity. Even on cosmic scales, the void is not small compared to the observable universe. It represents a significant fraction of the volume within several billion light-years of Earth. More troubling, we happen to live near the center of this abnormal structure, which seems to contradict the idea that our location is unremarkable. Throughout history, science has progressively removed Earth from any special position. Copernicus showed Earth was not the center of the solar system. Later observations showed the solar system was not the center of the galaxy, and the galaxy was not the center of anything. The cosmological principle is the ultimate expression of this trend. Not only is Earth not at the center, but there is no center because every location is equivalent. The void challenges that worldview. If we live inside an abnormally large, underdense region, our location is unusual by definition. Voids are common in the universe, but most are smaller than the KBC void. Supervoids this large are rare. Finding ourselves in one raises questions about whether the cosmological principle truly holds or whether it is only approximately true on scales much larger than previously thought. Some scientists calculate that in a universe governed by standard cosmology, a void as large and deep as the KBC void should be exceedingly rare, perhaps a 10 sigma statistical deviation. In a typical random realization of the universe's structure, you might not find one anywhere in the observable cosmos. Yet we are in one. This suggests either we are incredibly lucky or the standard model is wrong about how structure forms. Defenders of the cosmological principle argue that the void does not actually violate the principle because homogeneity only applies at scales of several hundred megaparsecs or larger. The void is about 600 megaparsecs across, which is right at the edge of where homogeneity is supposed to kick in. Maybe the universe is less smooth at those scales than we assumed. Alternatively, maybe the void is not as extreme as measurements suggest. Different observational techniques give somewhat different density contrasts for the void. If the true deficit is closer to 10 or 15% rather than 20%, the statistical rarity becomes less severe. These counterarguments preserve the cosmological principle but require accepting that our measurements are less precise than we thought. Another defense is that we should not be surprised to find ourselves in an unusual location because observers can only exist in certain types of environments. This is a weak anthropic argument. Perhaps intelligent life requires galaxies to form, and galaxies form preferentially in moderately dense regions rather than in the densest clusters or the emptiest voids. If most observers live in mildly underdense regions, then finding ourselves in a slight void is not surprising. But this argument only works if the KBC void is not as extreme as it appears. A 20% deficit is more than mild. It pushes the boundary of what the anthropic principle can explain away. The debate over the cosmological principle is not settled. Some researchers believe the void is real and significant, requiring either modifications to cosmology or acceptance that Earth occupies a genuinely unusual position. Others believe the void is an observational artifact or not as extreme as initially reported. Still others propose that the principle holds on even larger scales and that the apparent violation is temporary. Future observations should help resolve this. Surveys that map the universe to greater distances and depths will reveal whether large voids are as rare as standard models predict or whether they are more common than expected. If big voids turn out to be frequent, the cosmological principle survives, but the standard model needs revision. If they are truly rare, we need to explain why we happen to live in one. The origin of these voids reaches back to the universe's first moments. The voids we observe today began as infinitesimal quantum ripples in the first moments after the Big Bang. During a period called inflation, the universe expanded exponentially for a tiny fraction of a second, perhaps 10 to the minus 35 seconds. During this expansion, quantum fluctuations were stretched from subatomic scales to cosmic scales. These fluctuations created slight variations in the density of matter and energy. In some regions, density was a tiny bit higher than average. In others, it was a tiny bit lower. The variations were incredibly small, about 1 part in 100,000. But they were enough to set the stage for everything that followed. After inflation ended, the universe continued expanding but at a much slower rate. Matter began to clump together under gravity, but the gravitational pulling only amplified the initial density differences. Regions that started slightly denser attracted more matter from their surroundings, making them denser still. This created a positive feedback loop. The denser a region became, the more strongly it pulled matter toward itself. Over millions of years, these overdense regions collapsed into the first stars, then galaxies, then clusters of galaxies. Meanwhile, regions that started slightly less dense lost matter to their denser neighbors. As matter drained away toward the collapsing, overdense regions, the underdense regions became even emptier. These underdense regions evolved into voids. The process is called gravitational instability, and it turned barely perceptible initial ripples into the dramatic large-scale structure we observe today. The cosmic microwave background radiation provides a snapshot of these density variations when the universe was only 380,000 years old. At that time, the variations were still tiny, visible only as slight temperature differences of about 100 millionths of a degree. But those temperature differences correspond directly to density differences. Warmer spots had slightly higher density. Cooler spots had slightly lower density. Satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck spacecraft have mapped these temperature variations in exquisite detail across the entire sky. The maps show a modeled pattern of hot and cold spots at various angular scales. This pattern encodes the seeds of structure formation. Scientists can take this pattern and run it forward in computer simulations to predict how structure should look billions of years later. Those simulations reliably produce a cosmic web of filaments, clusters, and voids that closely resembles what we observe. The match between predictions and observations is one of the great successes of modern cosmology. It confirms that our understanding of how gravity shapes structure over cosmic time is largely correct. However, the simulations rarely produce voids as large or as deep as the KBC void. This is where tension arises. The initial quantum fluctuations were random, so every region had some chance of ending up as a void or a filament, but probability distributions matter. Small voids should be common. Medium voids should be less common. Extremely large voids should be very rare. The KBC void appears to fall into the extremely rare category, which raises questions about whether our simulations are missing something. One possibility is that the initial quantum fluctuations were not completely random but had subtle patterns that enhanced the formation of large voids. This could happen if inflation did not smooth out structure as uniformly as standard models assume. Another possibility is that gravity works slightly differently on large scales than general relativity predicts, which would change how voids form and evolve. A third option is that the universe simply has more variance in structure than cosmologists expected, making large voids less surprising. Each of these explanations requires further evidence. Observations of more distant voids in other parts of the universe would help determine how rare the KBC void truly is. If similar voids turn up frequently, it suggests the standard model underestimates structure variance. If they remain exceedingly rare, it strengthens the case for modified physics or unusual initial conditions. The quantum origin of voids is both elegant and unsettling. It means that the cosmic desert we inhabit traces back to subatomic processes that occurred before atoms even existed. Randomness at the smallest scales propagated upward to create structure at the largest scales. The universe's organization is not designed or predetermined. It is the consequence of random quantum fluctuations amplified by gravity over billions of years. This realization is one of the profound insights of modern cosmology. But it also means that our location within this structure is the result of chance. There is no reason we had to end up in a void rather than in a filament. We are here because the initial conditions in our region happen to be slightly underdense. That accident of quantum chance 14 billion years ago determines what we observe when we look out at the cosmos today. The scale of these empty regions dwarfs human imagination. When you picture the universe, you probably imagine a sky full of stars and galaxies. But the reality is the opposite. The universe is overwhelmingly empty. Voids occupy roughly 90% of the total volume of space. Galaxies and galaxy clusters crowd into the remaining 10%, packed into filaments and walls that surround the voids. This is not just empty space in the sense of vacuum between stars. It is empty in the sense that entire regions hundreds of millions of light-years across contain almost no galaxies at all. If you could travel through a void, you would fly for tens of millions of years at the speed of light without encountering a single galaxy. The isolation would be nearly absolute. This distribution creates a lopsided universe. Most of the matter concentrates in a small fraction of the volume. The filaments are crowded with galaxies that interact, merge, and evolve rapidly. Star formation is vigorous. Black holes grow. Galaxies collide and trigger bursts of star creation. Meanwhile, the voids are quiet. A few lonely dwarf galaxies drift through the darkness, separated by vast distances. These void galaxies evolve slowly because they rarely interact with neighbors. They tend to be smaller, fainter, and less evolved than galaxies in dense regions. Star formation is sluggish. Many void galaxies contain large amounts of neutral hydrogen gas that has not yet condensed into stars. They are galactic backwaters, isolated from the busy highways of the cosmic web. The extreme emptiness of voids raises questions about how empty space can really be. Even in voids, dark matter is present. Dark matter makes up about 85% of all matter in the universe, but does not interact with light, making it invisible to telescopes. It is detectable only through its gravitational effect. In voids, dark matter is much less concentrated than in filaments, but it still exists at about 15% of the cosmic average density. That might sound like a lot, but spread over such huge volumes, the amount of dark matter per cubic light-year is incredibly tiny. Additionally, voids contain dark energy, the mysterious component driving cosmic acceleration. Dark energy appears to be uniform throughout space. So, voids have just as much dark energy per volume as dense regions. In fact, because dark energy does not clump like matter, it becomes the dominant component in voids where matter is scarce. The interplay between dark matter and dark energy determines void evolution. In the early universe, matter dominated even in underdense regions, and gravity still mattered. As the universe expanded and dark energy became more important, voids began accelerating their expansion. This acceleration makes voids grow faster over time, eating into the surrounding filaments. Eventually, if dark energy continues to dominate, voids will consume more and more of the universe. Filaments will thin out. Galaxy clusters will become isolated islands in an expanding ocean of emptiness. Billions of years in the future, the universe will be even emptier than it is now, with voids occupying an even larger fraction of the total volume. This future evolution is inevitable given what we understand about dark energy. The universe's destiny is to become increasingly hollow. Understanding the void fraction of the universe is important for interpreting observations. When we measure the average properties of the universe, such as the overall matter density or the expansion rate, we are averaging over both voids and filaments. If we do not account for the fact that most space is void, we might misinterpret what those averages mean. For instance, measurements of the cosmic microwave background give the average matter density of the universe, which is about 30% of the critical density needed to stop cosmic expansion. But that average includes both the dense filaments and the sparse voids. The local density varies dramatically depending on where you are. In a filament, the density might be 3 times the average. In a void, it might be 15% of the average. These variations matter when trying to understand local observations. The 90% void fraction also affects searches for rare phenomena. For example, astronomers searching for distant supernovae or gamma-ray bursts are most likely to find them in the dense filaments where star formation is active. Finding these events in voids is much rarer because voids contain fewer galaxies and less star formation. This creates an observational selection effect. Most of the interesting astronomical events happen in the busy 10% of the universe, not the quiet 90%. We study the universe from within the active regions and mostly ignore the empty ones. But the voids are just as much a part of cosmic reality as the filaments. Understanding them is essential for understanding the universe as a whole. One void stands out as particularly impossible under current physics. The KBC void defies probability in a way that makes cosmologists deeply uncomfortable. Standard cosmology predicts that structures form through gravitational collapse of initial density fluctuations. The larger and deeper a structure, the rarer it should be. Small voids, a few tens of millions of light-years across, are common because they arise from common small fluctuations. Large voids hundreds of millions of light-years across are less common because they require larger, rarer fluctuations. The KBC void is 2 billion light-years across and 20% underdense. Computer simulations of structure formation using the lambda-cold dark matter model rarely produce anything this extreme. When researchers run thousands of simulated universes and look for voids as large and deep as the KBC void, they find very few matches. The statistical likelihood of such a void existing is extremely low. Some studies have estimated the improbability. One analysis calculated that a void of the KBC size and depth represents a 10 sigma deviation from the expected density. In statistics, a 5 sigma result means there is less than a 1 in a million chance of it being random. A 10 sigma result is incomprehensibly unlikely. You would need to observe trillions of universe-sized volumes to expect to find even one such void. Yet here we are living in one. This is not a small statistical anomaly. It is a massive red flag suggesting something is wrong with either the observations or the model. If the observations are correct, which multiple independent studies suggest they are, then the model must be missing something. One possibility is that the initial density fluctuations after the Big Bang were not as smooth as standard inflation models predict. If inflation produced more power on large scales than expected, large voids would form more easily. This would require modifying our understanding of inflation, which is already a speculative part of cosmology with limited direct evidence. Another possibility is that structure formation proceeded faster or differently than standard models predict. If gravity was effectively stronger in the past, or if dark matter behaves differently than assumed, structure would form more vigorously, creating larger voids and richer clusters. Some researchers propose modified gravity theories where the strength of gravity varies with scale or environment. These theories can enhance structure formation and make large voids more likely. A third option is that the KBC void is not as extreme as measurements suggest. Perhaps observational biases or systematic errors in galaxy surveys have made the void appear deeper and larger than it really is. Different groups using different data sets have measured the void's properties and found somewhat different results. Some studies find a 20% density deficit. Others find closer to 10 or 15%. If the true deficit is on the lower end, the statistical rarity becomes less severe. Though it remains a challenge for standard models, confirming the void's exact properties requires more data, particularly deeper galaxy surveys that can map the void's extent and density profile with higher precision. Future missions like the Euclid Space Telescope and the Vera Rubin Observatory will provide much better data. The existence of the KBC void has become ammunition in debates about the standard cosmological model. Critics of lambda-cold dark matter point to the void as evidence that the model fails on large scales. They argue that structure formation is not well understood and that the standard model makes incorrect predictions. Defenders of the model counter that rare events sometimes happen and that finding ourselves in a statistical outlier is not impossible, just unlikely. They also note that other aspects of cosmology, such as the cosmic microwave background, match lambda-cold dark matter predictions very well. Abandoning or significantly modifying the model based on one anomalous structure seems premature. Nevertheless, the void cannot be dismissed. It is a real observation that requires explanation. Either we accept that we happen to live in an exceptionally rare location, which violates the spirit of the cosmological principle, or we modify our models to make large voids more common, which requires changing fundamental assumptions about inflation, dark matter, or gravity. Neither option is satisfying. Both represent major shifts in how we think about the universe. The KBC void has become a focal point for cosmological debates precisely because it sits at the intersection of observation and theory, challenging our most basic assumptions about how the universe works. Until this tension is resolved, the void remains a cosmic puzzle that refuses to fit neatly into our current understanding. These vast empty regions serve an unexpected scientific purpose. Cosmic voids are the best places in the universe to study dark energy, because voids are the only regions where dark energy dominates completely. In dense areas like galaxy clusters, gravity is strong enough to resist cosmic expansion. Clusters hold themselves together gravitationally despite the universe expanding around them. Even on slightly larger scales and filaments, gravity is still relevant, slowing the expansion of space in those regions. But in voids, where matter is sparse, gravity becomes negligible. With no significant gravitational pull to counteract it, dark energy controls what happens. The voids expand faster than the cosmic average, driven by dark energy's repulsive pressure. This makes voids natural laboratories for measuring dark energy's strength and properties. Dark energy is one of the most mysterious components of the universe. Discovered in 1998 through observations of distant supernovae, dark energy accounts for about 68% of the universe's total energy. It behaves opposite to normal matter and gravity. Where gravity pulls things together, dark energy pushes space apart, accelerating cosmic expansion. The exact nature of dark energy remains unknown. It could be a cosmological constant, an unchanging energy density built into the fabric of space itself. Or it could be a dynamic field that varies in strength over time and space. Distinguishing between these possibilities requires precise measurements of how expansion accelerates in different environments and at different times in cosmic history. Voids provide a cleaner signal for these measurements than dense regions. In dense areas, gravity complicates everything. The local gravitational pull from nearby masses affects galaxy motions, making it hard to separate the cosmic expansion from local effects. In voids, those complications are minimal. Galaxies move almost entirely due to cosmic expansion and dark energy. By measuring how fast voids expand compared to predictions, scientists can test whether dark energy behaves as a constant or whether it changes. If dark energy is stronger in voids than elsewhere, or if it was different in the past, that would show up as deviations from expected void expansion rates. Another way voids help is through their shape. Dark energy affects not just how fast the universe expands, but also how it expands in different directions. If dark energy is truly uniform, voids should expand equally in all directions, staying spherical. But if dark energy has variations, or if there are other unknown forces, voids might expand more in some directions than others, becoming elongated or distorted. Observations of void shapes can therefore reveal whether dark energy is uniform or has structure. Current measurements show that most large voids are roughly spherical, which supports the idea that dark energy is uniform. But the measurements are not yet precise enough to rule out small variations. Improved surveys in the coming years will provide much better shape measurements. The expansion history of voids also encodes information about dark energy. Voids have been growing for billions of years, and their current size reflects that entire history. By modeling how a void should grow over time given different dark energy properties, scientists can compare predictions to observations and constrain what dark energy must be like. For example, if dark energy was weaker in the past and became stronger recently, voids would have grown slowly at first and then accelerated. If dark energy has been constant, voids should grow at a steady accelerating pace determined by that constant value. Observations of voids at different distances, which means different times in the past, allow testing these scenarios. One particularly useful technique involves measuring void edges. The boundary between a void and a surrounding filament is a transition zone where density rises sharply. This boundary evolves over time as matter drains out of the void and accumulates in the filaments. The sharpness and location of this edge depends on how fast the void is expanding, which depends on dark energy. By mapping void edges at different cosmic times and comparing them to simulations, researchers can infer how dark energy has influenced void growth. Early results suggest dark energy has been roughly constant over the past several billion years, consistent with the simplest models. But ongoing studies are refining these results and looking for any deviations that might hint at more complex behavior. Studying dark energy through voids is an active area of research. Future surveys will discover and characterize thousands of voids at various distances and sizes. Each void provides an independent measurement of dark energy's effects. Combining many measurements will dramatically improve our understanding. If voids reveal that dark energy is changing or has structure, that would revolutionize cosmology. Even confirming that dark energy is constant and uniform would be important because it would rule out many alternative theories. Either way, voids are proving to be essential tools for probing one of the universe's deepest mysteries. The KBC Void, being the largest and closest supervoid, offers the best opportunity for detailed study. Its proximity allows measurements that are impossible for distant voids. Galaxies that form within these cosmic deserts face unique challenges. Galaxies inside cosmic voids grow up in profound loneliness. Unlike galaxies in dense clusters that interact frequently with neighbors, void galaxies evolve in isolation. This environmental difference shapes everything about them. Void galaxies tend to be smaller and dimmer than galaxies in filaments. They have lower masses, containing fewer stars and less overall matter. Many void galaxies are classified as dwarf galaxies, barely massive enough to hold onto their gas against the outward pressure from star formation. Their isolation means they rarely experience the galaxy mergers that are common in dense regions. Mergers are a primary driver of galaxy evolution, triggering bursts of star formation and feeding central black holes. Without mergers, void galaxies evolve more slowly and remain less developed. The star formation rate in void galaxies is generally lower than in cluster galaxies. But there is a surprising twist. While most void galaxies form stars slowly, a higher fraction of them are starburst galaxies, experiencing intense short-lived periods of rapid star formation. This seems paradoxical until you consider the gas content. Void galaxies are often unusually gas-rich, containing large reservoirs of neutral hydrogen that have not yet been converted into stars. In dense environments, interactions with neighboring galaxies can strip away gas or trigger star formation, depleting the reservoir. In voids, galaxies retain their gas longer. When star formation does ignite, perhaps triggered by internal processes rather than external interactions, there is plenty of fuel available. The result is an intense starburst that consumes gas rapidly before settling back into quiescence. The morphology of void galaxies also differs. Most are late-type spirals or irregular galaxies rather than elliptical galaxies. Elliptical galaxies form primarily through mergers, which are rare in voids. Without mergers, galaxies maintain their disk structures and spiral arms. Some void galaxies show remarkably undisturbed morphologies with smooth disk profiles and regular rotation patterns. They have not been battered by interactions or gravitational tides from neighbors. This makes them excellent laboratories for studying how galaxies evolve in peaceful environments. Observations of void galaxies provide a baseline for comparison with the more chaotic evolution seen in dense regions. The dark matter halos around void galaxies are another interesting feature. Dark matter dominates the mass of every galaxy, forming a halo that extends far beyond the visible stars. In voids, these halos are subject to less external gravitational influence. They remain more spherical and undisturbed compared to halos in clusters, which often get stretched and distorted by tidal forces from neighboring halos. The simpler halo structure in voids makes them easier to model and study. However, the lowest mass halos in voids face a challenge. Below a certain mass threshold, roughly corresponding to a circular velocity of 35 kilometers per second, halos have too little gravity to retain gas efficiently. Star formation requires gas to cool and collapse, which happens more easily in deeper gravitational wells. The shallowest halos cannot form stars at all. This explains why voids are not completely filled with tiny dwarf galaxies. Below a certain mass, halos exist but remain dark, containing only dark matter and no visible galaxies. One puzzling aspect of void galaxies is their chemical composition. Stars create heavy elements through nuclear fusion, and when they die, they release these elements into space. Subsequent generations of stars incorporate these elements, gradually enriching the galaxy's overall chemical composition. This process is called chemical evolution. Void galaxies, with their slower star formation rates, should have lower chemical enrichment compared to galaxies in dense regions. Observations confirm this to some extent. Void galaxies tend to have lower metallicities, meaning less abundance of elements heavier than helium. But the difference is not as large as expected. Some void galaxies show chemical abundances surprisingly similar to galaxies in normal environments. This suggests chemical evolution is more complex than simple models predict, perhaps involving gas flows in and out of galaxies that redistribute elements. The evolution of void galaxies over cosmic time is an active research area. By observing void galaxies at different distances, which corresponds to different times in the past, scientists can trace how these galaxies have changed. Early results suggest void galaxies have been relatively stable, evolving gradually without the dramatic transformations common in clusters. This stability makes them valuable for understanding the intrinsic processes that drive galaxy evolution without environmental complications. Future surveys with improved sensitivity will discover fainter void galaxies and trace their properties across billions of years of cosmic history. These observations will test whether our understanding of galaxy formation is complete or whether void environments reveal processes we have missed. The giant structure containing all these scattered void galaxies is stranger still. The Laniakea supercluster is a mind-bending structure that redefines what we mean by our cosmic neighborhood. Identified in 2014, Laniakea contains roughly 100,000 galaxies spread across 520 million light-years. The name comes from Hawaiian and means immeasurable heaven, which is fitting given its scale. The Milky Way sits on the outskirts of Laniakea, part of a vast cosmic drainage basin where galaxies flow toward a central gravitational attractor called the Great Attractor. The entire structure moves coherently, bound together by gravitational flows that override cosmic expansion on these scales. Think of Laniakea as a watershed where matter flows downhill toward the deepest gravitational valley, except the terrain is the curvature of spacetime rather than literal landscape. Here is the paradox. Laniakea, despite containing 100,000 galaxies, resides entirely within the KBC Void. How can a supercluster, one of the largest bound structures in the universe, exist inside an underdense region? The answer lies in how density is defined. The KBC void is underdense compared to the cosmic average when measured over very large scales. But it is not uniformly empty. It contains filaments which contain clusters, which contain groups, which contain galaxies, which contain stars. Structure exists at every scale. The KBC void is primarily defined by the absence of rich superclusters and large galaxy clusters at its center. The edges of the void, where the density transitions to normal values, are hundreds of millions of light-years away from us. Within that enormous volume, there is still plenty of matter, just not as much as there should be on average. Laniakea occupies part of that volume. It is large compared to typical superclusters but small compared to the void itself. The gravitational flows within Laniakea provide some of the best evidence for how gravity organizes matter. By mapping the velocities of galaxies in and around the supercluster, astronomers constructed a three-dimensional flow map showing how matter moves through space. Galaxies closer to the Great Attractor are falling toward it faster. Galaxies at the edges of Laniakea are just beginning to feel its pull. These flows define Laniakea's boundaries. Everything moving toward the Great Attractor is considered part of the supercluster. Everything flowing away from it belongs to neighboring structures. The Milky Way's peculiar velocity points toward the Great Attractor, confirming we are gravitationally bound to Laniakea. But Laniakea itself is falling toward something even larger. The Shapley supercluster, located about 650 million light-years away, is the most massive structure in our region of the universe. It contains tens of thousands of galaxies and has a gravitational pull strong enough to affect everything around it, including Laniakea. The entire Laniakea supercluster is moving toward Shapley at several hundred kilometers per second. This creates a hierarchy of flows. Galaxies flow toward clusters. Clusters flow toward superclusters, and superclusters flow toward even larger attractors. The KBC void modifies these flows by adding an outward component. Galaxies are simultaneously falling toward local attractors like the Great Attractor and flowing outward away from the void center. The combination produces complex velocity patterns. Understanding Laniakea's structure and motion helps clarify our position within the KBC void. We are not at the void center in complete isolation. We are offset from the center, situated in a moderately dense region that is nonetheless underdense compared to cosmic averages. Laniakea represents a significant concentration of matter within the void. But it is not enough to eliminate the void's overall underdensity. The paradox resolves when you realize that large-scale and small-scale structures coexist. The void describes the average properties over billions of light-years. Laniakea describes the local properties over hundreds of millions of light-years. Both are real and both matter for different aspects of cosmology. The measurements revealing all of this rely on a cosmic ruler built from sound waves in the infant universe. Baryon acoustic oscillations are frozen sound waves from the early universe, and they have become the most reliable ruler for measuring cosmic distances. In the first 380,000 years after the Big Bang, the universe was a hot plasma where matter and radiation were coupled together. Sound waves rippled through this plasma, creating oscillations in density. When the universe cooled enough for atoms to form, the sound waves froze in place. The distance these waves traveled before freezing left an imprint on how matter is distributed today. That distance is about 490 million light-years, and it shows up as a characteristic scale in the clustering of galaxies. Astronomers can measure this scale and use it as a standard ruler because the physics that created it is well understood. This ruler works at any distance. Whether you look at galaxies nearby or billions of light-years away, the same characteristic scale appears in their distribution. By comparing the apparent size of this scale at different distances, scientists can map how the universe has expanded over time. It is like placing identical meter sticks at various distances and measuring how big they appear. If the universe's expansion is accelerating, distant meter sticks look smaller than they should. If expansion is slowing, they look larger. The technique is called Baryon acoustic oscillation analysis, and it has revolutionized distance measurements in cosmology. Unlike other methods that rely on the brightness of objects, which can be affected by dust or other complications, the Baryon acoustic oscillation scale is purely geometric. Using this technique, researchers have mapped the three-dimensional distribution of galaxies across billions of light-years. These maps reveal the cosmic web in unprecedented detail. They also reveal the KBC Void. When scientists analyze galaxy distributions in our local region and compare them to predictions from Baryon acoustic oscillations, they find a clear deficit. The void shows up as a region where the observed scale of galaxy clustering differs from what distant measurements predict. This mismatch is exactly what you expect if you are inside an underdense region. The Baryon acoustic oscillations provide independent confirmation that the void exists and quantify its depth and extent. The measurements are not simple. Mapping galaxy distributions requires massive surveys that observe hundreds of thousands of galaxies and measure each one's position and redshift. Projects like the Sloan Digital Sky Survey and the Baryon Oscillation Spectroscopic Survey have spent years collecting this data. Processing it requires sophisticated statistical analysis to extract the Baryon acoustic oscillation signal from the noise of random galaxy positions. The signal is subtle, typically only a few percent stronger clustering at the characteristic scale compared to other scales, but modern surveys are sensitive enough to detect it reliably. In the void, galaxies show redshifts that are slightly higher than expected for their distance when using the Baryon acoustic oscillation ruler. This is consistent with the outflow velocity adding to the cosmic expansion signal. The Baryon acoustic oscillation measurements thus provide another piece of evidence for the void and its impact on our observations. They show that the Hubble tension is not confined to supernova measurements but appears across multiple independent techniques. The precision of Baryon acoustic oscillation measurements continues improving with new surveys. The Dark Energy Spectroscopic Instrument, which began operations in 2021, is mapping tens of millions of galaxies with unprecedented accuracy. These measurements will allow much finer mapping of the void structure and velocity field. Within a few years, astronomers will know the void's properties to within a few percent uncertainty. That precision will either confirm the void as the explanation for the Hubble tension or reveal additional complications that require further theoretical development. Either way, Baryon acoustic oscillations are proving to be an essential tool for understanding our cosmic environment. The temperature of the universe itself reveals the void's fingerprint. The cosmic microwave background radiation fills the entire universe with faint light left over from the Big Bang. This temperature is remarkably uniform at 2.7 Kelvin, just above absolute zero. But that uniformity is not perfect. Tiny temperature variations exist, typically only a few millionths of a degree different from one direction to another. These variations encode information about the early universe's structure. Hot spots correspond to regions that were slightly denser. Cold spots correspond to regions that were slightly less dense. Satellites have mapped these temperature variations across the entire sky with exquisite precision, revealing the seeds of structure formation. But the cosmic microwave background also reveals something else. It shows evidence of cosmic voids. Light from the cosmic microwave background has traveled through 13.8 billion years of cosmic evolution to reach us. During that journey, it passes through the structures that formed along the way, including voids. When light enters a void, it experiences less gravitational influence than light passing through dense regions. This creates a measurable effect called the integrated Sachs-Wolfe effect. As a photon falls into a slightly less dense region, it gains a tiny bit of energy from the gravitational potential. As it climbs back out, it loses energy. Normally, these effects would cancel perfectly. But if the void is expanding while the photon is passing through, which happens because of dark energy, the cancellation is not perfect. The photon ends up with slightly less energy than it started with, which shows up as a temperature drop. This effect is tiny but detectable when you average over many voids. Astronomers have identified the locations of large voids in the nearby universe using galaxy surveys. They then looked at the cosmic microwave background temperature in those directions and found that, on average, the temperature is about 10 millionths of a degree cooler than the cosmic average. The correlation is statistically significant and matches predictions from theory. It confirms that voids do affect the cosmic microwave background through the integrated Sachs-Wolfe effect. For the KBC void specifically, the effect should be particularly strong because of its size. Light from the cosmic microwave background passes through nearly the entire void on its way to us, accumulating the temperature deficit over the full billion light-year extent. One of the most intriguing features in the cosmic microwave background is the cold spot, discovered by the Wilkinson Microwave Anisotropy Probe. This region is about 5 degrees across on the sky and appears roughly 100 millionths of a degree cooler than surrounding areas. It is unusually large and cold compared to typical fluctuations expected from the early universe. One explanation is that the cold spot results from a supervoid along that line of sight. If a particularly large and deep void happens to lie in that direction, it could create the observed temperature deficit through the integrated Sachs-Wolfe effect. Some researchers have searched for such a void in galaxy surveys and found weak evidence for an underdensity in that region. However, the connection remains controversial because the supervoid needed to explain the cold spot would itself be statistically unlikely. The KBC void does not align with the cold spot. It surrounds us in all directions rather than appearing in one specific direction. Its temperature signature is therefore more subtle, showing up as a modification to the overall cosmic microwave background pattern rather than a localized anomaly. Detecting this signature requires careful modeling of what the cosmic microwave background should look like with and without the void. Preliminary analyses suggest the void's presence is consistent with the observed cosmic microwave background. But the signal is not yet definitive. Future measurements with higher sensitivity should clarify whether the void leaves a detectable imprint on the cosmic microwave background temperature distribution. The temperature measurements also constrain the void's properties. If the void were much deeper or larger than current estimates, it would create a stronger temperature signal that should already be visible. The fact that no dramatic anomaly appears in the cosmic microwave background in our direction places upper limits on how extreme the void can be. These limits are consistent with a 20% density deficit extending about 1 billion light-years, which matches other measurements. The cosmic microwave background thus provides an independent check on the void's existence and properties. It is reassuring that multiple independent lines of evidence all point to the same basic picture. We live in a large underdense region with significant but not extreme properties. The void's existence has led some scientists to question whether gravity itself needs revision. The standard theory of gravity is Einstein's general relativity, formulated in 1915. It has passed every test thrown at it for over a century, from predicting the bending of light around massive objects to explaining the orbital decay of binary pulsars. General relativity forms the foundation of modern cosmology. But the KBC void challenges this foundation in unexpected ways. If the void is too large and too deep to arise naturally in simulations based on general relativity and lambda cold dark matter, perhaps gravity does not work exactly as Einstein predicted on the largest scales. Some scientists propose modifying gravity rather than accepting we live in a statistically improbable location. Modified Newtonian dynamics, or MOND, is the most prominent alternative gravity theory. Proposed in 1983 by physicist Mordechai Milgrom, MOND suggests that gravity behaves differently when accelerations are extremely small below a certain threshold. At high accelerations, like those on Earth or in the inner solar system, gravity follows Newton's laws and Einstein's corrections exactly. But at the tiny accelerations relevant for galaxy outskirts and cosmological scales, gravity becomes stronger than general relativity predicts. This modification was originally proposed to explain galaxy rotation curves without invoking dark matter. Galaxies spin faster than visible matter can account for. Either there is invisible dark matter providing extra gravity, or gravity itself is stronger at large distances. MOND has struggled to explain many cosmological observations, but it performs better than expected at explaining some features of the cosmic web. In MOND cosmology, structures form more efficiently because the enhanced gravity on large scales pulls matter together more effectively. This produces richer superclusters and deeper voids compared to standard gravity. Computer simulations using MOND gravity naturally create voids as large as the KBC void without requiring unusual initial conditions. The statistical improbability disappears. The void becomes an expected consequence of how structure forms under modified gravity. This is an attractive feature because it resolves the tension between observations and theory without invoking extreme luck. However, MOND faces serious challenges. It struggles to explain the cosmic microwave background temperature fluctuations, which standard cosmology explains beautifully using general relativity. MOND also cannot easily account for gravitational lensing observations where massive galaxy clusters bend light from background galaxies. The amount of lensing observed requires more gravity than visible matter plus MOND's modification can provide, suggesting dark matter is still needed. Some researchers have developed hybrid models that combine MOND with a small amount of dark matter, typically in the form of neutrinos. These models, called neutrino hot dark matter cosmologies, can explain both the cosmic microwave background and the enhanced structure formation seen in the cosmic web. Another class of modified gravity theories involves changing how gravity propagates over large distances rather than changing its strength. These theories, collectively called modified gravity theories, introduce additional fields or higher dimensional effects that alter gravitational dynamics on cosmological scales while preserving general relativity's successes on smaller scales. Some of these theories predict that gravity becomes effectively stronger in low-density regions like voids, which would make large voids easier to form. Testing these theories requires precise measurements of how matter moves in voids versus dense regions. If the velocity patterns deviate from general relativity's predictions, it could indicate modified gravity at work. The debate between modified gravity and standard cosmology with a statistically unlikely void remains unresolved. Proponents of modified gravity argue that repeatedly finding structures that are too large or too rare according to standard models indicates the models are wrong. They point to the KBC Void, the Shapley Supercluster, the Sloan Great Wall, and other enormous structures as evidence that structure formation is more vigorous than lambda-cold dark matter predicts. Defenders of standard cosmology argue that modified gravity theories have their own problems and that invoking them to solve one puzzle often creates new puzzles elsewhere. They prefer to accept that we live in an unusual location rather than overthrowing a century of successful gravitational physics. Future observations should help settle this debate. If large voids and extreme structures turn out to be more common than currently thought, modified gravity becomes more appealing. If they remain rare, the standard model survives but leaves us with the uncomfortable conclusion that Earth occupies a special location. Either way, the KBC Void has become a battleground where fundamental physics is being tested. The void's existence threatens our calculations of cosmic age. The age of the universe is one of cosmology's most important numbers, and the KBC Void puts it in jeopardy. Current measurements based on the cosmic microwave background place the universe's age at 13.8 billion years. This number comes from detailed models of how the universe expanded from the Big Bang to the present. The models use the cosmic expansion rate measured from the cosmic microwave background, along with other parameters like matter density and dark energy density. Together, these parameters determine how long ago the Big Bang occurred. The result has been verified by multiple independent analyses and is considered highly reliable. But if the local expansion rate is genuinely faster than the cosmic average due to the void, those models could be wrong. Here is the problem. If the Hubble constant measured locally, about 73 kilometers per second per megaparsec, represents the universe's true expansion rate rather than a void-distorted local value, then the universe has been expanding faster throughout its history. A faster expansion rate means the universe reached its current size in less time. Calculations show this would make the universe about 8% younger, roughly 12.7 billion years old instead of 13.8 billion years. That may sound like a small difference, but it creates major conflicts with other observations. The oldest stars in globular clusters appear to be about 13 billion years old based on stellar evolution theory. You cannot have stars older than the universe itself. This conflict has led to intense scrutiny of stellar age measurements. The ages come from understanding how stars evolve over time. Stars of different masses burn through their nuclear fuel at different rates. Low-mass stars last hundreds of billions of years. High-mass stars exhaust themselves in just millions of years. By observing which stars have reached the end of their lives in a globular cluster, astronomers can estimate when all the stars in that cluster formed. The oldest clusters show that their most massive remaining stars are just barely still alive, indicating the clusters formed about 13 billion years ago. These measurements depend on understanding stellar physics, which is well tested but not perfect. Small uncertainties in how stars burn hydrogen or how they evolve off the main sequence could shift age estimates by hundreds of millions of years. Some researchers argue that if stellar ages are uncertain enough, they might accommodate a younger universe. Perhaps globular clusters are actually 12.5 billion years old rather than 13 billion years old, which would fit with a younger universe. But this requires assuming current stellar models are systematically wrong in just the right way, which seems contrived. Other scientists point out that stellar ages are not the only constraint. White dwarf cooling times provide an independent age measurement. White dwarfs are the remnants of dead stars that cool gradually over billions of years. The coolest white dwarfs we observe have been cooling for about 12 to 13 billion years, again suggesting the universe is at least that old. These measurements do not depend on stellar evolution models, making them harder to adjust. The age tension, like the Hubble tension, might be resolved if the local expansion rate does not represent the global average. If the void inflates our local measurements, the cosmic microwave background estimate of 13.8 billion years could be correct. After all, the universe would be old enough for the observed stars and white dwarfs to exist. This resolution requires accepting that we live in an unusual location, which bothers some scientists philosophically, but it avoids requiring major changes to stellar physics or cosmology. Alternatively, both measurements could be partly right if dark energy has evolved over time. If dark energy was weaker in the past and became stronger recently, the early expansion would have been slower, and the universe would be older than the high local Hubble constant suggests. This scenario is speculative but not ruled out. The age issue highlights a broader problem in cosmology. Many of the parameters we measure are interconnected. Changing the expansion rate affects not just the universe's age but also the density of matter, the properties of dark energy, and predictions for structure formation. You cannot adjust one parameter without affecting others. This makes resolving tensions difficult because fixes in one area often create problems in another. The KBC Void offers a way to preserve most of the standard model by attributing discrepancies to our unusual location, but it does not eliminate the age tension completely because some evidence for the universe's age comes from objects within the void itself. These local age measurements should be unaffected by the void's impact on expansion measurements. Yet they align more closely with the cosmic microwave background age than the local Hubble constant age. This internal consistency suggests the void explanation, while appealing, may not tell the whole story. Ancient starlight creates another problem for void-based solutions. The oldest stars in our galaxy pose a stubborn challenge to any cosmological model that makes the universe significantly younger. These ancient stars, found primarily in globular clusters and the galactic halo, contain very little metal. In astronomy, metal means any element heavier than helium. The first stars in the universe formed from pure hydrogen and helium left over from the Big Bang. They created heavier elements through nuclear fusion and scattered them into space when they died. Subsequent generations of stars incorporated these metals, gradually increasing the metallicity of the galaxy. The most metal-poor stars we observe today must have formed very early, before much metal enrichment occurred. Their ages tell us directly how long ago the galaxy formed. Measuring stellar ages requires understanding stellar structure and evolution. Stars spend most of their lives burning hydrogen in their cores, a phase called the main sequence. The time a star spends on the main sequence depends on its mass. Massive stars burn through their fuel quickly. Low-mass stars burn slowly. When a star exhausts its core hydrogen, it evolves off the main sequence, expanding into a red giant and undergoing further evolutionary stages. By observing a cluster of stars born at the same time, astronomers can see which masses have evolved off the main sequence. This turn-off point reveals the cluster's age. The faintest stars still on the main sequence indicate how long hydrogen burning has been occurring, directly measuring the time since formation. Globular cluster ages derived this way consistently come out to around 12.5 to 13 billion years. The uncertainty is a few hundred million years, mainly from uncertainties in stellar physics, like how efficiently stars mix their internal material or how much mass they lose through stellar winds. But the measurements are consistent across many clusters using different techniques. The Gaia space mission has revolutionized these measurements by providing precise distances to globular clusters through parallax measurements. Knowing the exact distance allows determining absolute brightness, which removes one major uncertainty from age calculations. The improved measurements confirm that the oldest clusters are indeed about 13 billion years old. This creates a problem if the universe is only 12.7 billion years old, as the high local Hubble constant suggests. You cannot fit 13-billion-year-old stars into a 12.7-billion-year-old universe. The numbers simply do not work. Some resolution is required. Either the stellar ages are wrong, the universe's age is wrong, or both are partly wrong in compensating ways. The stellar age measurements are robust enough that major errors seem unlikely. They are based on well-tested physics and confirmed by multiple methods. The universe's age based on the cosmic microwave background is also robust, depending on a completely different set of physics. This leaves the high local Hubble constant as the most likely culprit. If that measurement is inflated by the void, the contradiction disappears. However, the situation is more subtle. The oldest stars are local objects within the Milky Way. If the KBC void significantly affects our measurements of the universe's properties, should it not also affect our interpretation of these stars? Some researchers argue that it should not, because stellar ages depend on local physics like nuclear reaction rates, not on cosmic expansion. The age of a star is determined by how long it has been burning hydrogen, which is unaffected by whether we live in a void. Other researchers counter that the initial conditions for star formation in our galaxy depend on when the galaxy formed, which depends on cosmic history. If the void affected structure formation in our region, the first stars might have formed earlier or later than in typical regions. This debate touches on a fundamental question. How much does our local environment affect local observations versus cosmic observations? Measurements of distant supernovae and the expansion rate are clearly affected by the void because they involve light traveling through the void and peculiar velocities within it. But measurements of objects within our galaxy should be largely unaffected because they depend only on local physics. The age tension might therefore indicate that the high local Hubble constant is not just a void effect but a genuine global tension requiring new physics. Alternatively, it might indicate that our understanding of stellar evolution needs refinement. The issue remains unresolved and will require additional observations and theoretical work to clarify. The motion of galaxies across vast distances adds yet another complication. Galaxies are not stationary. They move through space in response to gravity from surrounding structures. These motions are called peculiar velocities because they are peculiar to each galaxy, distinct from the overall cosmic expansion. In standard cosmology, peculiar velocities should be relatively small and random on large scales. Nearby galaxies might move at a few hundred kilometers per second due to local gravity. But when you average over volumes hundreds of millions of light-years across, those peculiar velocities should largely cancel out. The average motion, called bulk flow, should be close to zero. This is what homogeneity predicts. If the universe is truly uniform on large scales, there should be no coherent large-scale flows because there are no large-scale gravitational gradients to drive them. Observations tell a different story. Measurements of galaxy velocities using multiple techniques show significant bulk flows extending to distances of 200 to 300 million light-years. These flows reach velocities of 400 kilometers per second or more, far higher than standard cosmology predicts. For such large scales, the flows are coherent, meaning galaxies across huge volumes are all moving in roughly the same direction. This suggests the presence of large-scale structure producing gravitational gradients that pull matter in specific directions. The KBC void is exactly the kind of structure that could produce such flows. Material within the void is accelerating outward toward denser regions beyond the void's edges. This creates a bulk flow pointing away from the void center. Measuring bulk flows is challenging because it requires accurate distance estimates for many galaxies. Redshift alone is not enough because it mixes cosmic expansion with peculiar velocity. You need independent distance measurements that do not rely on redshift. Techniques like Tully-Fisher relations for spiral galaxies and fundamental plane relations for elliptical galaxies provide these distances by comparing the distance-based velocity to the redshift-based velocity. Astronomers can extract the peculiar velocity. Compiling measurements for thousands of galaxies allows mapping the large-scale velocity field. The Cosmic Flows project has done exactly this, creating the most detailed maps of bulk flows to date. The observed bulk flows match predictions from models that include the KBC void. When researchers simulate how galaxies should move if they are inside a large underdense region surrounded by overdense shells, the predicted velocities and flow patterns closely match observations. The flows are strongest near the void edges where the density gradient is sharpest. They are directed outward from the underdensity toward the surrounding filaments. The magnitude of the flows depends on the void's depth and size. A 20% density deficit extending 1 billion light-years produces flows of about 400 kilometers per second, exactly what is observed. This agreement is striking and provides strong support for the void hypothesis. Standard cosmology without a void struggles to explain these flows. Simulations based on lambda cold dark matter predict bulk flows should decline rapidly with scale. By the time you average over 200 million light-years, bulk flows should be under 100 kilometers per second. The observed flows are 4 times larger. You can increase the predicted flows by assuming more structure than typical, but that requires invoking rare density fluctuations, which brings back the same statistical improbability issue that the void represents. Either way, the observations point to more structure on large scales than standard models comfortably predict. Some cosmologists view this as evidence that lambda-cold dark matter is missing something, either in its treatment of dark matter, dark energy, or the gravitational physics governing structure formation. Alternative theories like modified gravity naturally predict stronger bulk flows because they enhance structure formation. In Mond cosmology, for example, the effective gravitational strength on large scales is higher, creating deeper potential wells and stronger flows. The observed bulk flows are consistent with predictions without requiring statistically unlikely structures. This has led some researchers to favor modified gravity as a more natural explanation for both the KBC void and the associated bulk flows. However, modified gravity has other difficulties, so the debate continues. Upcoming surveys will measure bulk flows at even larger distances and with greater precision. If flows remain strong beyond 300 million light-years, it would further challenge standard cosmology. If they decline as expected, it would suggest the KBC void is an isolated feature rather than indicative of systematic problems with the model. The bulk flow observations underscore a theme emerging throughout this story. Our local cosmic environment is more dynamic and structured than simple homogeneous models assume. The universe on large scales may not be as smooth as the cosmological principle requires. Whether this means we live in an unusual location or whether it means our models need revision depends on how these observations develop. The KBC void and its associated flows are at the center of this unfolding story. An even larger void exists elsewhere in the cosmos. The KBC void is not the largest underdense region known. That distinction belongs to the Eridanus supervoid, discovered through its impact on the cosmic microwave background. Located in the constellation Eridanus, this void is roughly 1.8 billion light-years across, making it slightly smaller than the KBC void but comparable in scale. What makes the Eridanus supervoid particularly intriguing is how it was found. Astronomers did not discover it by counting galaxies. They discovered it by noticing an unusually cold spot in the cosmic microwave background temperature map. This cold spot, about 10 degrees across on the sky, corresponds to a region where the microwave background is about 70 millionths of a degree cooler than average. That is much colder than typical fluctuations from the early universe. The cold spot, as it is called, was discovered by the Wilkinson Microwave Anisotropy Probe in 2005. Its existence puzzled cosmologists because its size and temperature deficit are statistically unusual. Random fluctuations from the early universe should occasionally produce cold spots, but one this large and cold is rare, occurring in only about 2% of simulated universes. Some researchers initially proposed exotic explanations, including the possibility that it represented a collision between our universe and another universe in a multiverse. More prosaic explanations suggested it might be a random statistical fluke or an artifact of how the data was processed. But the cold spot persisted in multiple independent datasets, including observations from the Planck satellite. A more conventional explanation emerged when astronomers surveyed the galaxy distribution in the direction of the cold spot. They found evidence for a large underdense region roughly aligned with it. This void, later named the Eridanus supervoid, sits about 3 billion light-years away. Light from the cosmic microwave background passes through this void on its way to Earth, experiencing the integrated Sachs-Wolfe effect. As the light traverses the expanding void, it loses energy, showing up as a temperature deficit. Calculations show that a void of the Eridanus supervoid size and depth can account for about half of the observed cold spot temperature anomaly. The other half might come from a chance alignment with a cold fluctuation in the primordial cosmic microwave background. Or it might indicate the void is larger and deeper than current measurements suggest. The Eridanus supervoid raises the same questions as the KBC void. How did such a large, underdense region form? Is it consistent with standard cosmology, or does it require unusual initial conditions? The void's existence was predicted by the cosmic microwave background cold spot before it was confirmed by galaxy surveys, which gives researchers some confidence in its reality. But measuring its precise properties remains difficult because it is so distant. Galaxy surveys at that distance are less complete than nearby surveys. Many faint galaxies are missed, making it hard to quantify the exact density deficit. Current estimates place the deficit at about 20 to 30% compared to cosmic average, similar to the KBC void. If both the KBC void and the Eridanus supervoid are real and as extreme as measurements suggest, It raises the likelihood that such voids are more common than standard cosmology predicts. Two large supervoids in the observable universe might still be consistent with lambda-cold dark matter if you allow for some statistical variance. But finding 3 or 4 would become increasingly difficult to explain. Future deep surveys will map the universe to even greater distances and discover more voids. The statistical distribution of void sizes and depths will test whether structure formation matches predictions. If large voids are common, it suggests either we misunderstand structure formation or we live in an atypical part of the universe where large voids happen to cluster. Neither option is comfortable. The Eridanus supervoid also demonstrates that voids affect observations in measurable ways. The temperature deficit they create in the cosmic microwave background is small but detectable. The velocity fields they generate are observable through bulk flow measurements. These effects are not just theoretical predictions. They are real phenomena that astronomers can study. This gives researchers hope that the mysteries surrounding the KBC void and the Hubble tension can eventually be resolved through better observations. If voids systematically affect measurements in known ways, those effects can be corrected for or modeled. The challenge is obtaining sufficient data to characterize the void structure of the universe accurately. One thing is clear: the universe contains more large voids than early cosmological models anticipated. Whether this reflects the rarity of our cosmic neighborhood or inadequacies in our models remains an open question. Our measurements are only reliable when we look far beyond our local region. The term Hubble Bubble has emerged to describe a troubling observational pattern. When astronomers measure the Hubble constant using nearby objects like supernovae within about 2 billion light-years, they get higher values around 73 kilometers per second per megaparsec. When they use objects farther than 2 billion light-years or rely on cosmic microwave background data, they get lower values around 67 kilometers per second per megaparsec. The boundary at roughly 2 billion light-years is suspiciously close to the edge of the KBC void. This has led researchers to propose that measurements within the void are affected by its presence, creating a bubble of biased observations. Only by looking beyond the bubble can we see the universe's true expansion rate. This hypothesis makes a clear prediction. The measured Hubble constant should vary with distance. Nearby measurements should show the highest values. As you look farther out, approaching and crossing the void's edge, the measured value should decline toward the cosmic average. Beyond 2 billion light-years, it should stabilize at the lower value. This is exactly what recent observations are beginning to show. Studies using supernovae at various distances find that the inferred Hubble constant decreases with redshift. The trend is not yet definitive because measuring distances to very distant supernovae is challenging and uncertainties are large. But the direction of the trend matches predictions from the Hubble bubble hypothesis. If the bubble is real, it creates a significant problem for cosmology. Most measurements of the local expansion rate necessarily use nearby objects because those are the only ones we can observe in sufficient detail. Distant objects are fainter and harder to characterize precisely. This means our most reliable local measurements are exactly the ones most affected by the void. We are trapped inside the bubble, unable to step outside our local environment to see what the universe truly looks like. It is like trying to determine the climate of Earth by only measuring the temperature inside a heated building. You can make very precise measurements, but they do not represent the global average. Breaking out of the bubble requires observing objects beyond 2 billion light-years with comparable precision to nearby objects. This is technologically challenging but becoming possible. Space telescopes like the James Webb Space Telescope can observe distant supernovae with unprecedented detail. Ground-based observatories with enormous mirrors and advanced instruments are discovering quasars and other bright objects at extreme distances. These distant probes offer a window into the universe outside the bubble. Early results suggest the far universe expands at the rate predicted by the cosmic microwave background, consistent with the bubble hypothesis. But the data are still limited. More observations are needed to confirm the trend and establish whether it fully resolves the Hubble tension. The bubble concept also applies to other measurements. Bulk flow observations show significant motions out to about 300 million light-years but appear to decline at larger distances. This is consistent with the void creating a local velocity field that dissipates as you approach the void's edge. The Baryon acoustic oscillation measurements show discrepancies primarily at low redshift, again suggesting local effects. Multiple independent lines of evidence point to the same conclusion. Our local environment within about 2 billion light-years differs systematically from the universe at large. We live in an island of unusual properties surrounded by a more typical cosmos. Accepting the Hubble Bubble hypothesis requires accepting that many of the measurements we use to understand the universe are biased by our location. This is philosophically uncomfortable. Scientists prefer to believe their observations are representative of universal truths rather than local accidents. But the evidence increasingly suggests we cannot escape our local bias without looking far enough away that the void's influence fades. Future surveys that probe the universe beyond 2 billion light-years will be crucial for confirming whether the bubble is real and whether it fully explains the Hubble tension. If it does, cosmology can breathe a sigh of relief. The standard model works fine. We just happen to be measuring from a weird spot. If the tension persists even at large distances, new physics will be required. The void does more than skew measurements. It affects the very possibility of structure forming within it. Cosmic voids act as filters, preventing certain types of structures from forming within them. In dense regions of the cosmic web, galaxies collide and merge frequently. Small galaxies combine into larger ones. Gas is stripped from galaxies by interactions with hot intracluster gas. Supermassive black holes in galaxy centers grow by accreting material stirred up by mergers. These processes drive rapid evolution, transforming small, irregular galaxies into massive elliptical galaxies over billions of years. Galaxy clusters form as groups merge together under their mutual gravity. Rich clusters containing thousands of galaxies emerge, surrounded by hot X-ray emitting gas. This is the normal trajectory of structure formation in dense environments. But in voids, this trajectory is blocked. The low density in voids means gravity is weak. Small structures like galaxies can form because the initial density fluctuations that seeded them were strong enough to overcome cosmic expansion. But larger structures like massive galaxy groups or clusters require more gravity than voids can provide. The matter density is simply insufficient to pull together such massive concentrations. As a result, voids remain perpetually underdeveloped. The largest structures that form within them are modest galaxy groups containing a few dozen members. Richer clusters cannot form. This creates a ceiling on structure development. Voids are stuck in an evolutionary state that dense regions passed through billions of years ago. This filtering effect has consequences for galaxy evolution. In dense environments, galaxies experience frequent mergers that consume their gas and shut down star formation. The galaxies become red and dead, filled with old stars but forming few new ones. This process, called quenching, transforms star-forming spiral galaxies into passive elliptical galaxies. But in voids, mergers are rare. Galaxies retain their gas and continue forming stars slowly over billions of years. They remain blue and actively star-forming much longer than their counterparts in clusters. This explains why void galaxies tend to be late-type spirals with ongoing star formation rather than early-type ellipticals dominated by old stars. The filter also affects the intergalactic medium, the diffuse gas between galaxies. In dense regions, this gas is heated to millions of degrees by shocks from galaxy collisions and by energy output from supermassive black holes. The hot gas emits X-rays and is easily detected. In voids, the intergalactic medium remains cooler and denser, closer to the conditions in the early universe. This makes voids excellent laboratories for studying primordial gas and how it gradually gets incorporated into galaxies. The cooler gas in voids is more likely to contain neutral hydrogen, which can be detected through its radio emission. Surveys of neutral hydrogen in voids have revealed filamentary structures of gas connecting the few galaxies present, remnants of the cosmic web on small scales. The filtering effect is self-reinforcing because massive structures cannot form in voids. The void environment remains unchanging. There are no rich clusters to pump energy into the intergalactic medium. There are no massive galaxies to drive strong galactic winds that expel gas. The void remains quiet and underdeveloped indefinitely. Meanwhile, dense regions continue evolving, becoming richer and more complex. This creates increasing contrast between voids and filaments. The universe's structure becomes more extreme over time, with voids getting emptier and filaments getting denser. Dark energy accelerates this trend by speeding up void expansion. The Great Filter concept has implications for life in the universe. If advanced civilizations require certain environmental conditions, such as stable galaxies with ongoing star formation, voids might be more hospitable than dense regions. Void galaxies experience fewer catastrophic events like nearby supernovae or gamma-ray bursts that could sterilize planets. The isolation provides long-term stability. On the other hand, the low rate of star formation in voids means fewer heavy elements available for planet formation. Void galaxies tend to be metal-poor, which might limit the types of planets that can form. Whether voids enhance or diminish the prospects for life is an open question. But if we live in a void, it might influence the galaxy we find ourselves in and the conditions that allowed Earth to develop. The future of voids is one of increasing isolation. Dark energy is accelerating the universe's expansion, and that acceleration has dire implications for the far future. As space expands faster over time, structures that are not gravitationally bound together will drift apart and eventually lose all contact. This process is already happening, but it will intensify over the coming billions and trillions of years. Voids will expand faster than the universe as a whole because they contain less matter to resist the expansion. The filaments surrounding voids will thin out as galaxies within them are stretched farther apart. Eventually, even neighboring superclusters will lose causal contact as space between them expands faster than light can cross. The universe's fate is increasing isolation, with structures becoming islands separated by ever-expanding voids. For galaxies within voids, this isolation will be profound. Currently, galaxies in the KBC Void can still see the surrounding filaments and clusters in the distance. Light from those structures reaches us after traveling for billions of years. But as dark energy drives accelerating expansion, light from increasingly distant objects will never reach us. The cosmic horizon, the boundary beyond which light cannot reach us before the universe expands too much, will shrink over time. Objects currently visible will fade from view as their light gets redshifted into invisibility. Galaxies deep within voids will find themselves in increasingly empty skies with fewer and fewer neighbors visible. The cosmic microwave background radiation will become cooler and dimmer as its photons stretch to longer wavelengths. Eventually, it will become undetectable. This raises a disturbing question for future civilizations. If a civilization arises in a void galaxy billions of years from now, what will they be able to learn about the universe? Their sky will be nearly empty except for their local group of galaxies. The cosmic microwave background will be too faint to detect. There will be no evidence of the Big Bang, no distant galaxies to measure cosmic expansion, no supernovae to trace the acceleration. They will be cosmologically isolated, unable to observe the larger universe because light from beyond their immediate vicinity cannot reach them. Such civilizations might conclude they live in a static island universe surrounded by empty space, never suspecting the vaster cosmos beyond their horizon. This scenario, sometimes called the dark future, is the inevitable consequence of accelerating expansion. Even within our own void, the long-term future looks lonely. The Milky Way and Andromeda will merge in about 4 billion years, forming a giant elliptical galaxy sometimes called Milkomeda. This merged galaxy will be the dominant structure in our local group. But the local group itself will become increasingly isolated. Other nearby groups like the Leo Spur or the Virgo cluster will recede beyond our cosmic horizon within tens of billions of years. Milkomeda will find itself essentially alone in an expanding void. Star formation will gradually cease as gas is consumed or expelled. The galaxy will fade, containing only old red stars and eventually just white dwarfs, neutron stars, and black holes. The night sky will darken as fewer stars remain active. On even longer timescales, trillions of years into the future, stars will become rare as their fuel is exhausted. Galaxies will consist mainly of dead stellar remnants slowly evaporating into space through gravitational interactions. Black holes will dominate, slowly growing by accreting whatever material remains. Eventually, even black holes will evaporate through Hawking radiation, a quantum process that causes them to lose mass over incomprehensibly long timescales. The final state of the universe will be a diffuse sea of particles and radiation expanding forever into darkness. Voids will have consumed everything, with the last remnants of structure dissipating into the void's infinite expanse. This bleak future is billions of years away and depends on dark energy continuing to accelerate expansion. If dark energy changes in strength or sign, the future could be different. But current observations suggest dark energy is a cosmological constant, unchanging and unrelenting. If so, the universe's ultimate fate is void domination. The cosmic web we observe today with its intricate filaments and clusters is a temporary phase. The true long-term structure of the universe is emptiness punctuated by isolated islands of matter that grow ever more remote from each other. We live in an unusual time when the universe still has rich structure and when voids are features rather than the dominant reality. Billions of years hence, voids will be everything. One final question remains about our position within this cosmic void. If we live inside a cosmic void, are there other civilizations in the same predicament? This question connects to the broader search for intelligent life in the universe. The distribution of matter affects where life can emerge. Galaxies need sufficient heavy elements to form rocky planets. Those elements are created by stars and scattered through space by supernovae. Stellar explosions or gamma-ray bursts could sterilize planets within thousands of light-years. Active galactic nuclei in cluster galaxies pump enormous energy into their surroundings, potentially disrupting planet formation. Voids offer a quieter environment where galaxies evolve peacefully. Stars form at a moderate pace. Planets have billions of years to develop life, and cataclysmic interruptions are rare. This might make void galaxies ideal nurseries for complex life. The lower metallicity could be offset by the longer timescales available for chemical enrichment to occur naturally through stellar evolution. Arguments against void favorability focus on resources. Void galaxies tend to be smaller and less massive. They form fewer stars, meaning fewer opportunities for planets to develop. The lower metallicity means the first planets to form are gas giants with few rocky worlds. Life as we know it requires complex chemistry involving carbon, oxygen, nitrogen, and other heavy elements. These elements are scarcer in voids. Additionally, the isolation of void galaxies might limit the spread of life if panspermia, the transfer of life between star systems, plays a role. In dense regions, material ejected from one planetary system might seed another nearby. In voids, the vast distances between stars and galaxies make such transfers nearly impossible. Each void galaxy would have to develop life independently. If other civilizations exist in voids, would they develop the same understanding of cosmology that we have? This is a fascinating question. A civilization in a dense cluster would observe rich structure in every direction. Their sky would be crowded with nearby galaxies. They would easily discover cosmic expansion and the Hubble constant because they could observe a large sample of galaxies at various distances. For them, the Big Bang model would be natural and quickly accepted. But a civilization deep inside a void might struggle. With few nearby galaxies to observe, measuring cosmic expansion becomes challenging. The void's effect on local measurements could confuse them, leading to incorrect conclusions about the universe's properties. They might develop alternative models explaining their observations without invoking cosmic expansion or dark energy. This raises the meta-question of whether our own cosmology is affected by our void location in ways we have not yet realized. We think we understand the universe fairly well based on observations from within the KBC Void. But what if there are systematic biases we have not accounted for? What if the universe beyond the void looks fundamentally different from what we observe locally? Future observations extending well beyond the void will test this. If distant regions confirm our local conclusions, we can feel confident our understanding is correct. If they reveal systematic differences, we may need to revise our entire cosmological framework. This is the ultimate test of whether void dwellers can accurately understand the cosmos or whether we are forever limited by our unusual vantage point. The search for life in the universe has traditionally focused on habitable zones around stars, the detection of biosignatures in exoplanet atmospheres, and the search for technosignatures like radio transmissions from advanced civilizations. Perhaps it should also consider the large-scale environment. Civilizations in voids might be more common if voids provide stable conditions, or they might be rare if voids lack sufficient resources. Either way, the cosmic web structure influences where we should look. If we are typical of void civilizations, other intelligent species might also wonder whether their cosmological measurements are distorted by their location. They might also be searching for signals from beyond their local void, hoping to contact civilizations with different perspectives on the universe. We are inside a cosmic hole 2 billion light-years wide. This is not metaphor or speculation. This is observation. The KBC void is real. Its effects are measurable, and its existence challenges fundamental assumptions about cosmology. Whether it explains the Hubble tension, whether it requires modified gravity, Whether it makes us unusually positioned in the universe, these questions remain open. But one thing is certain. The universe is far stranger than we imagined, and our place within it is more unusual than we ever suspected. We are cosmic castaways, drifting through a desert of space, measuring a universe that may not be what it seems. Thanks for watching this deep dive into the cosmic void we call home. If you enjoyed this video, please give it a like and subscribe to the channel for more mind-blowing science and space content. Share your thoughts in the comments below. Do you think we live in a cosmic void? And what does that mean for our understanding of the universe? And don't forget to hit that notification bell so you never miss an upload. Until next time, keep looking up and never stop questioning what lies beyond.